Okay, welcome class to Physics 390, class 16. This class is on helium and the periodic table. And it will come from chapter 5.2 of the textbook. We'll be looking at helium and dealing with it as a very complicated system with two electrons and the electron-electron interactions, and looking at how we can get a grip on helium by approximating it and ignoring the electron-electron interactions. And we'll also be looking at the periodic table and how the higher elements than helium with greater atomic numbers have their the electrons fill the available energy states and the consequences that has for the periodic table in chemistry. So helium, the approximate two electron ground state. So helium has a Hamiltonian, which is given by this here. It's got a kinetic, so it has two electrons, so it's a two particle Hamiltonian. This first term here has the kinetic energy, this term here, and the potential energy with respect to the helium nucleus. So notice we have, instead of E squared as for the hydrogen atom, we have 2E squared because the helium nucleus has charge 2. So it's 2E squared. And then for the second electron, we have similar interactions. We have the kinetic energy term and the potential energy term here with respect to the nucleus. And then we have the electron-electron energy term, which is 1/4πε0 E squared over the distance between the two electrons. And if the interaction was just these first four terms, then we could split the two particle Schrodinger equation into two equations and solve it with some work. Similarly, if it was just two electrons, so it was a central force between the two electrons, we could solve that two particle Schrodinger equation. But when we combine them together, we get something pretty complicated. So we have to approximate. So, and the electron-electron term then makes solving for the wave function psi of R1 and R2, the two electron wave function, analytically impossible. So it's just not possible to solve with this Hamiltonian. But we can still get some insight. So if we ignore the electron-electron term, we can find an approximate helium ground state, psi of R1, R2, as the hydrogen state, NLM of R1 for electron 1, times the hydrogen state N prime L prime L prime M prime of R2. And for the helium ground state, NL and M would be 1, 0, 0, the lowest hydrogen ground state, and hydrogen state, and N prime L prime would similarly be 1, 0, 0. So the approximate helium ground state would be just the product of these hydrogen stationary states, the ground state for electron 1 in the hydrogen atom times the ground state for electron 2 in the hydrogen atom. Multiplied together, if we ignore the electron-electron term, gives us the approximate helium ground state. Now, the energy of this ground state is actually E equals, you might think it would just be the energy of these two hydrogen states, but it's actually 4 times that. Or since each of these ground states for n equal 1 is minus 13.6 electron volts, it would be 8 times minus 13 electron volts, or minus 109 electron volts. So why is it bigger? Well, the factor of 4 comes from the fact that in the expression for En for the hydrogen atom, if we include the charge on the nucleus, the Z of the nucleus comes in with a square on it. And since helium has atomic number Z equal 2, when we put in z squared, that gives a factor of 4. And so we have 4 times the energy that we would have for the hydrogen. So this is the prediction for the helium ground state, the approximate helium ground state, minus 109 electron volts. So how does that stack up? Oh, also the approximate ground state is symmetric. If we look at this ground state here, if we switch R1 and R2, we get the same thing back again. So it's the spatial state is symmetric. So we expect the 2-particle spin state to be antisymmetric, known as the singlet state, where one, roughly speaking, one electron is spin up and the other is spin down. So how does that stack up with what is measured in the atomic experiments? Well, the spin state of the actual helium ground state is in fact a singlet state. So our model gets that right. But the energy of the actual ground state is minus just a little under 70, or a little over minus 79 electron volts. So we miss by about, let's see, minus 109, minus 79, about 40 electron volts. But notice that we miss in the actual ground state is more positive energy than the approximate ground state. And that makes sense because the electron energy, which we ignored in getting the approximate helium ground state, is positive. And that electron energy, because the electrons repel each other and so have a positive potential energy, can account for the 40 electron volt difference. Okay, so that's how we can make an approximate ground state to electron ground state for helium and compare it to the actual ground state. And we do okay. But of course, the electron energy is important and has an effect on the helium ground state. Okay, what about the excited states for helium? So the excited states for helium consist of putting 1 electron in a ground state and 1 electron in an excited state. Now you might say, why can't you put both in excited states? Well, if you do that, one of the electrons in the excited states will jump down to the ground state and give off energy, and that will actually bump the other electron in the excited state out of the helium atom, resulting in ionization of the helium atom. So we don't have a helium atom anymore, we have a helium ion. And we want a neutral helium atom here. So we just have 1 electron in a ground state and 1 in an excited state. So we can construct both symmetric and anti-symmetric excited states, and they would look like this. So we have, this is the symmetric. So the two electron wave function for helium would be with this normalization factor 1/√2. An excited state NLM for the first particle, the ground state for the second particle, plus NLM for the second particle times the ground state for the first particle. And you can see that this is symmetric. If you switch R1 and R2, we get the same thing back again. And the anti-symmetric would be the same thing, except we have 1/√2, the same thing with a minus sign. So if we switch R1 and R2 here, we get the negative of, so psi R2 R1 is minus psi R1 R2, as it should be for an anti-symmetric spatial excited state. Okay, so these would be paired with the symmetric spatial excited state would be paired with an anti-symmetric, that is a singlet 2-particle spin state. So this one here would be paired with the singlet state, and the anti-symmetric spatial excited state would be paired with the symmetric, one of the triplet 2-particle spin states. And there are 3 of those. So this is a triplet. And this is to give a total wave function that is anti-symmetric. We pair the symmetric space with anti-symmetric spin to get a total anti-symmetric, or a anti-symmetric space with a symmetric spin to get a total anti-symmetric. And we need total anti-symmetric because the electrons are fermions. So when we switch the 2 coordinates, we should get a minus sign for the total wave function. So there's terms here, the symmetric space and antisymmetric spin states are known as perihelium. So if we have a symmetric space state, this guy right here, it's known as a perihelium state. Whereas the antisymmetric space, so this one right here, and the symmetric spin states are known as orthohelium, okay? That's just a terminology that arose in the study of helium. Perihelium states have somewhat higher energies because the symmetric spatial state tends to have the electrons closer together. And if the electrons are closer together, we expect a higher electron-electron potential energy since they repel each other, leading to a higher potential energy and a higher energy. So perihelium states, for a given excited state, if we build a symmetric state out of the ground state and a given excited state, the symmetric state will have a higher energy than the equivalent antisymmetric state, the equivalent orthohelium state. Okay, so that's the helium excited states. We have perihelium and orthohelium, and we build it out of a ground state and one excited state, either in symmetric or spatial, antisymmetric spatial excited states. All right, so what about the periodic table and the filling of orbitals? Well, for atoms with higher atomic number Z, so past helium like lithium, beryllium, and so forth, boron, if we ignore electron interactions again, just to get a first ballpark figure, the electrons will just fill up single particle hydrogen states, which we call, just for short, we call orbitals. That's what they call them in chemistry, and we also use that term in physics. So now bosons, if electrons were bosons, they could all share the ground orbital because bosons can all occupy as many bosons as we want can occupy a single quantum state. But as fermions, electrons can have at most 2 electrons in a given orbital. 2 because there's the spin state. So we can have a spin, roughly speaking, a spin up and a spin down in the same spatial orbital. So as a result, we quickly fill up the ground orbital, which has 2 electrons in it. So we have to go to the first excited state already with Z equal 3, which would be lithium. So there are many excited orbitals in the many electron ground states of atoms with higher Z. So going on into carbon, oxygen, nitrogen, there are many excited orbitals. So with higher numbers of N, higher numbers of L, and so forth. And this gives rise to the richness and complexity of chemistry in the periodic table, because we have all these different electrons with all these different energies occupying these different orbitals, interacting with each other in interesting ways and giving rise to the uniqueness of each, the chemistry of each element. And giving rise to, for example, carbon, which is the basis of life. So, so specifically, there are n squared orbitals with principal quantum number n. So if you count up all the, remember n is the principal quantum number, L and M are the, for hydrogen, are the other quantum numbers. And if you count up all the L and M's that are consistent with a given n, you get n squared orbitals. So in general, the nth so-called shell, so that all the orbitals with a given n number could hold 2 n squared electrons. N squared orbitals, 2 electrons per orbital, so 2n squared. So if that's the case, the shells should have, let's see, 2n squared. So for n equal 1, that's 2. For n equal 2, 2n squared would be 2 times 4 is 8. For n equal 3, it would be 2 times n squared, which would be 2 times 9 or 18. 2 times 4 squared is 32, 2 times 5 squared is 50 electrons in them, okay? So we expect the shells, as they fill up, to have these number of electrons in them. Instead, if we look at how the shells fill up, if you look at a periodic table, the shells fill up with 2, 8, 8, 18, 18, 18 electrons in them. Clearly some relationship to the expected, but some differences from that. And that kind of makes sense because we, in finding these numbers, we've ignored the electron-electron interactions. We've just assumed that the electrons are filling up these these shells or these orbitals independently and not interacting with each other. But the electron-electron repulsion modifies how the electrons fill the available states. In general, a higher value of the quantum number L raises the energy. This is because greater angular momentum tends to move the electron further from the nucleus. And the nucleus is screened more by inner electrons and has a lower effective charge, and so binds the electron less tightly. So again, having a higher quantum number L means we have more angular momentum. The electron spends more time away from the nucleus. So away from the nucleus, there's more electrons, inner electrons in between this outer electron and the nucleus. So it sees a lower effective charge because it's the inner electrons act to cancel part of the nuclear charge. And so that smaller effective nuclear charge binds the electron less tightly. And so that's a less, that's not as negative a number since it's not as bound. So it raises the energy. So as a result, states with lower values of L are filled first because we fill lower energy states first. And if higher quantum numbers have higher energies, they would get higher L's would get filled last. So the order in which orbitals are filled is complicated, but in general, it follows what we can call the N plus L rule, where orbitals with lower values of N plus L are filled first. So for example, the lowest value of N plus L would be N equal 1, L equals 0. That would give a total of 1. And hydrogen and helium, both the electrons in helium both fill up N equal 1, L equals 0. The next choice would be N equal 2. And for N equals 2, we can have L equals 1 or L equals 0. But N plus L would be lower if for N equals 2, L equals 0. So for lithium, and which is the third element, Z equal 3, it fills up the N equal 2, L equals 0 state first, rather than the 2, 1 state. Even though the hydrogen, in terms of just the energies of just the hydrogen atom, the 2, 0 state and the 2, 1 state have equal energies. When it's combined, when there are multiple electrons, the lower values of L are filled first. And so you can see our text for a detailed account of this. As we move through lithium and beryllium and boron and carbon and so forth, there's an order in which these orbitals are filled, generally following this N plus L rule, but with some exceptions because of these complicated electron-electron interactions. Okay, so we've looked in this video at the helium atom, an approximate ground state for the helium atom, with a symmetric spatial function and an anti-symmetric or singlet spin function or spin wave function. And we get decent agreement with the actual helium atom, but with a more bound, neglecting the electron-electron interaction energy makes our energy more negative. And then we looked at the excited states of helium. For the excited states of helium, we see that we have one electron in a hydrogen ground state, one in a hydrogen excited state. And we can form either symmetric or antisymmetric pairs of combinations of those ground state and excited state. And the one is called perihelium, the other is called helium, orthohelium. And then finally, for the periodic table, we see that roughly speaking, we fill up in order of n, but because of electron repulsion, that gets modified. And it's actually, the order is filled up in really order of n plus L, approximately speaking. Okay? And that gives rise to all the richness and interest of chemistry. Okay, thank you for your attention, and I will see you in class.